Hello, I'm JW, and in this video we're going to look at cables, or more specifically what happens when cables are overloaded. Now in a previous video, and several others in fact, I've had a look at fuses and various protective devices, and the primary purpose of those is to prevent the cables from being damaged by overheating. And the idea, of course, say with a fuse, is that the fuse wire will melt long before the cable does. But of course, if someone removed the fuse wire and just put a nail or some other unsuitable thing in there, and of course that's not going to melt, and the cables almost certainly will overheat, and of course could actually set on fire. Hence why it's not a good idea to use the incorrect materials in the fuse holder. So what we've got here is a piece of cable. This is actually 1mm, or 1 square millimetre, and it's twin and earth cable. And just have a look in that in a little more detail. And we'll put various currents through this and see how it will fare. Now here we have the cable we're going to be using. This is twin and earth cable. It's a common type of cable used in the UK for fixed wiring inside buildings. And it's got two insulated conductors here. These are solid copper and with a PVC insulation on there, blue and brown in this case. And it also has a single other conductor in the centre, which is normally used for the earth, and that's uninsulated, hence the twin and earth, of course. And overall it's covered in this grey outer covering. This insulation is PVC, and the grey covering is also PVC. And typically these are rated to maximum temperature of 70 degrees centigrade. Anything above that will cause damage to the cable, and in reality you wouldn't want to be running it at 70 degrees centigrade anyway for any length of time. What we've got here, say, is a 1mm cross-sectional area, or 1 square millimetre, and it's about 1 metre in length. This end I've just bared the two ends there. We're not going to be using that centre conductor, just the two insulated ones. And at the other end here I've actually just twisted the two conductors together, effectively creating a short circuit. So the current will flow in via one, through here, then of course back to the other end and into the power supply, which will connect to these two conductors. Now all of these cables of course have current ratings, and this table shows the ratings for this particular cable. So the size we're using is actually the smallest available size, 1 square millimetre there. And notice that there's different tables here depending on how the cable is installed, and this is primarily due to the amount of heat that the cable can dissipate. Obviously if it's in a wall it's going to be not dissipating very much heat, but on the other hand if it was just stuck on a surface or hanging in free air, it would be able to dissipate a lot more heat and therefore take more current. In this case we'll just be using it laying on a surface, so that will be the reference method C here, effectively just on a surface there. And as you can see here, it's rated to 15 amps, which is quite a lot actually, considering this is normally used on 6 amp lighting circuits. So if we'd hung it up in the air it would be 17, and that's purely due to the extra airflow over the cable, which would allow it to dissipate the heat more easily. Now of course all cables will heat up when current is passed through them, simply the fact that any wire, this being say copper, it has a fairly low resistance, but nevertheless it does have a small resistance. And of course if you pass current through resistance, then inevitably heat will be given off, and of course that's the principle of a heating wire. But of course in the case of these you want to make sure that that's low enough so that you don't have the thing melting or setting on fire. So we'll go outside and we'll start out with around 15 amps to see what happens, probably not a lot, and of course then we'll increase the current above that and see what goes wrong. So here we are outside, and here's the fairly simple test setup. The current is provided via that thick yellow lead at the top left, and you see it passes through the clamp meter, which will display the current. And the smaller meter there, the black one, is the temperature. That's actually in degrees centigrade. Actually it's just showing there 15, which is pretty much the outside temperature at the moment. And I've just taped the sensor onto the cable there with a bit of that green and yellow tape there, just to fix it on in place. The cable itself is connected via that large green clamp at the top there. The wire actually goes under the clamp and then comes back into it to connect there. And the other connection is made by that clamp showing at the lower edge of the picture there, and also we'll just clamp that onto that blue wire to make the circuit. So we can see the current on the meter there, and the temperature, obviously that should increase as current passes through the wires. Now to start with we'll use a 15 amp or approximately current, so we'll just connect up there, see a bit of a spark there, and see the current there is about 14.3 amps or so. And bearing in mind this is actually the rating for this cable, which was 15 amps before, so theoretically nothing should actually happen. See the temperature just gone up by 1 degree there, so that's hardly anything surprising. Of course even at the rated temperature the cable will heat up a bit. That's simply due to the fact that it has a certain amount of resistance. So now we're at 17 degrees centigrade, so again hardly anything unexpected. And see the temperature is slowly rising, but again nothing surprising there. So That is exactly what you'd expect, the rated current of course being 15 amps, and that's what we put through there. So let's try increasing that current and see what happens. Now this time we've got the current set to around 25 amps, just see it's just over the 25 amp mark there, and this is of course representing about a 10 amp overload for the particular cable. Temperature's about 20 degrees centigrade, so again hardly anything surprising there. And of course the temperature will slowly increase, now up to 22 and 23. Again, it's hardly setting on fire or causing a total disaster. Now obviously if we left this current on for an extended time, the cable would get pretty warm. But again, that's going to take quite a considerable time to do, as most of the heat going in is simply being dissipated into the air. Now notice the current has actually fallen slightly to 24.8 there, and that's due to the increased resistance in the wires as they heat up. Now this time we'll try a current of 50 amps, that's 50, so substantially more than it should be. And current there is 56 amps to start with. And temperature starting there about the 27 Celsius, and you notice the temperature is increasing rapidly, already up to 32 there, and of course this presents a pretty heavy duty overload for this particular cable. But again, it's not actually destroying itself instantly, there is still a considerable amount of time, by which time of course any fuse should have blown by now. Now temperature is actually approaching 60 degrees centigrade, and now coming up to the 70, after which the cable of course is going to be damaged because it's only rated for about 70. I know some smoke is coming off of the blue part of the wire there. Temperature is increasing, and the rest of the cable is actually softening quite considerably, and there's bits of smoke coming out of various areas, so clearly this isn't what you want to be happening inside your house. And of course as the current increases, smoke is now coming off of all of the cable as it gets beyond the point of no return. And now you see the wires are being exposed inside as the insulation melts and falls away. The temperature is now exceeding 200 and is rapidly increasing, so obviously we're going to have to just switch this off in a moment because this is getting out of hand. So as you can see there, that's 50 amps, and that really has totally destroyed the cable. Smoke billowing away in the wind there. Notice however that the cable didn't set on fire instantly. So although it was 50 amps, if a fuse or whatever had activated within say 3 or 4 seconds, the cable would not have actually been damaged in this case. Now just have a look at the cable, and as you can see it's totally destroyed there. Its insulation has gone very brittle and it's actually started to scorch and char the cardboard that it's resting on. Clearly if this had happened inside your house, the only option would be to replace the entire lot. Now this time we've got a new piece of cable, and this should be around 100 amps, so just connect on. So 115 amps or so there, and you see the temperature's climbing rapidly on the temperature gauge. Smoke is already billowing out of the wires, and of course the cable is now totally destroyed. Now just disconnect that there, and you'll see that the temperature is still increasing, and this is because the probe is in contact with the plastic insulation. And of course the heating of the wires takes a few seconds to actually penetrate through that insulation. So though the power's long gone, the temperature's still rising, well over 170 Celsius there. And as you can see, the cable is totally destroyed, and of course that only took literally just a few seconds from the current being applied. And finally we'll try the maximum available current from this machine, which is in the rate of 140 odd amps. And I haven't bothered with the thermocouple this time because it's pretty obvious what's going to happen. So let's just connect on and see how long it takes. So as you saw there, smoke and of course flames as well, and the wire has actually broken at the other connector there, and it's actually spot welded itself to the clamp at the lower edge of the picture. Now of course if that happened in your house, it would have set fire to your house more than likely by now. Clearly something that you want to be avoiding. So that's what happens to cables when they're overloaded. And notice on that last example, it was literally just a couple of seconds before smoke and flames literally billowed from the cable. And you might be thinking, well, even if you shoved a nail instead of that 5 amp fuse, there's of course the 100 amp supplier fuse inevitably going to break. But of course not necessarily, because the current that flows through the fault all depends on the impedance of that fault. and particularly on a lighting circuit where it could be of moderate length, it's certainly not implausible that you might have, say, a total impedance of, say, 2 or 3 ohms on that, and in which case only a current of about 100 amps is going to flow there, so your main fuse into the building is probably not going to blow at all. And even in the case of, say, 150 amps there, the main fuse is not going to break straight away. It will still maintain the current for several seconds. And as we saw there, several seconds is easily enough to completely destroy the cable and, of course, make it emit vast amounts of smoke and even set on fire. So clearly not putting the correct fuse in there is a very bad idea, because at best the entire circuit cable is going to be totally destroyed and need to be replaced. And of course at worst your house will burn to the ground and turn into a pile of ash. So until next time, thanks for watching.